In this lecture, we will cover three topics. One is the Clausius statement of the second law, and we will demonstrate that it's equivalent to the Kelvin-Planck statement already covered. And these two put together will demonstrate the impossibility of a perpetual motion machine. So there's a long title, but there are three brief issues we will address in this lecture. In the previous lecture, we talked about refrigeration and heat pumps. Both involve transfer of heat from a low temperature reservoir to a high temperature reservoir. Okay, so refrigeration and heat pump differ in terms of the objective. Here you want to remove heat, here you want to supply heat, but the operational principles are very similar. They're cyclical devices which take up heat from a low temperature reservoir, dump it to a high temperature reservoir, and this requires a work input. Work input here, work input here, and so on. Okay, so to calibrate the efficiency of these devices, we define something called coefficient of performance. Okay, so here there is this desired input divided by the required input, which is work. Okay, so none of this can operate, none of these devices can operate without this work input. So work input is always a finite quantity, it is never zero. If it is zero, the coefficient of performance will be infinity. So even otherwise, the coefficient of performance can be greater than 1. So we avoid using the term efficiency of refrigeration or efficiency of heat pump. So we use this formula for coefficient of performance. Both these things are related in a particular manner. So this formula is obtained by substituting the first law consideration, relating the net work to net heat transfer, and you can derive formula. This is fairly simple algebra. I'm not going to elaborate this here again. So all these things have been put together in a statement of Clausius. What is the central fact here? This cannot be zero, right? In both these cases, this cannot be zero. So that's the statement of Clausius. This is also a version of second law. It states that it is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a low temperature body to a high temperature body. There are two things you have to be noting. So one is, it's again a negative statement. Okay, so a negative statement cannot be proved. So, however, there is no experiment that disproves this negative statement. Okay, so that's the first thing. And what exactly we mean here by no effect? Okay, so the no effect, when we are referring to the effect, we are referring to the work input. Okay, so the environment in the case operation of the refrigerator or a heat pump, the environment supplies some work. Okay, so without that work input, you cannot transfer heat from a cold place and dump that heat to a hot place. So that work is always a finite quantity, it cannot be zero. Right? So that's the statement of second law. It's an equivalent statement it's an equivalent statement of second law. So violation of one of these statements, that is violation of, for example, a Kelvin-Planck statement, implies the violation of Clausius, statement of Clausius. Let's see how. What is the Kelvin-Planck statement? If you remember, we were talking about a heat engine. If the heat engine can completely convert heat to work, okay, without rejecting any heat to a low temperature reservoir, that means the heat engine operates at 100% efficiency and it violates Kelvin-Planck's statement, right? So supposing you imagine two devices operating in tandem, that is the heat engine plus the refrigerator. This work that gets out of the heat engine is provided to a refrigerator, and that is utilized for taking this heat from a low temperature reservoir and putting it into a high temperature reservoir. Okay, so this is the work input from a heat engine that is operating at 100% efficiency. But if you look at the entire system put together, you would see that the effective amount of heat that is being transferred from the low temperature reservoir to a high temperature reservoir is QL, right? So here QH is removed, here QH plus QL is being supplied here, right? So overall, QL is being removed from a low temperature reservoir, and we are managing to supply it to a high temperature reservoir via a refrigerator, which is violation of the Clausius statement. Okay, so a violation of the Kelvin-Planck statement implies the violation of the statement of Clausius. Let us look at it in a different way. Violation of Clausius statement also implies the violation of Kelvin-Planck statement. Let's see how this is done. For example, if you want to violate Clausius statement, what exactly do you mean? You take QC from a cold reservoir, you completely reject that to a hot reservoir without a work input. Okay, so that's a violation of the statement of Clausius. And then you operate in tandem a heat engine. What does the heat engine do? You supply QH, you remove supply to this engine, you remove heat QH from the high temperature reservoir, and you dump QC into a cold reservoir, and effectively applying first law here, you get work equivalent to QH minus QC. So what have you managed to do? If you take this at two devices operating in tandem, you would see there is no net transfer of heat to the cold reservoir. What you managed to do is QH minus QC amount of heat has been completely converted to work, okay, which is a violation of Kelvin-Planck statement. Okay, so both these things together, okay, violating one of the statement implies the violation of the other statement of second law. Okay, in a way that both are equivalent statements of second law. One is elaborated in the context of heat engine. The other statement, the Clausius statement, is elaborated in the context of refrigerator and heat pumps. We'll move on to perpetual motion machine. Okay. So if you look at history of engineering, especially energy engineering, there have been lots and lots of patents in energy which violates the first law of thermodynamics and second law of thermodynamics. Okay, so the US Patent Office has explicitly stated that any device that violates first and second law cannot be patented. Okay, so more of this is elaborated in your textbook, Chengel and Bullis. It's an interesting read, and there are very innovative, creative innovators who seems to have beaten the system and come up with the device, but there is a flaw in the device. Okay, so here what we have is a perpetual motion machine. This machine violates the first law of thermodynamics. Let's see how. Okay, so this machine is somehow started. What does this have? So this is a cyclically operating system. So this operates cyclically. It is connected to a electrical generator. So somehow you start the machine. Part of this electrical work is supplied to the boiler. Okay, this is like an ohmic resistor. This evaporates this fluid. Okay, so the heat required for the boiler is supplied from this electrical motor, and then this machine circulates, it operates in a cyclical manner. So once it operates, everything seems to be fine, right? So you have a boiler here that generates, let's say, steam, rotates a turbine, rotates a motor, and then you get to a condenser. Condenser, again, molecules are condensing, forming chemical bonds. Heat is being released, and then there is a fluid that is formed. You have a pump. Everything operates in a cyclical manner. But if you see, what you managed to do is that without supplying changes in internal energy, what you managed to get is net work out of the system and net heat out of the system. Okay? So this is violation of first law of thermodynamics. So it is impossible to operate such a machine. Okay, so this machine cannot be operated because it violates the first law of thermodynamics. Okay, so it looks as if you can, once it starts, you can continue to generate work and heat, but this is a violation of first law of thermodynamics. So there are other kinds of machines which obey the first law of thermodynamics, but violate the second law of thermodynamics. These are called perpetual motion machine of the second kind. So what are we seeing here? Okay, so what this device does is it eliminates the condenser. What, if you remember, what does the condenser do? It condenser rejects heat to a cold reservoir, thereby decreasing the efficiency, right? So here, what we have managed to do is remove that condenser, thereby there's no rejection of heat to a low temperature reservoir. So this seems to operate in a cyclical manner, and the boiler accepts heat from some source, and this obeys first law of thermodynamics. Why so? Because your delta U is 0, because it's a cyclical device. There is the net heat transfer is equal to the net work transfer. Okay, so here there is power. We are talking in terms of heat input and work on input per unit time. So even though it obeys the first law of thermodynamics, it violates the second law of thermodynamics. In what manner? All of heat is converted to work, okay, without any rejection to a cold temperature reservoir. Okay, so this violation of second law. These perpetual motion machine, which cannot really operate, they are called perpetual motion machine of the second kind. So what we would see in the next lecture are some other issues, certain irreversibilities in the system that also affect the efficiency of your devices. To explain them, it is easy to contrast them against reversible processes. So we have already seen what exactly we mean by thermodynamically reversible, but again, we will contrast reversible and irreversible processes and discuss these issues in the context of efficiency of devices and second law of thermodynamics. We will see that in the next lecture. Thank you.